Hi, this is Dr. T again. I'm here to kind of give you a quick summary of our lecture today, um, lecture 17. We previously have talked about molecular shape and molecular vibrations, and today we're going to talk about atmospheric gases and some atmospheric data, the carbon cycle, and then in a subsequent video we're going to talk about atomic and molecular mass, moles, and how we can use those to predict the impact of human activities on the environment to some extent. At least certainly be able to predict how much carbon we're putting into the environment. So the first thing I want to do is remind you that it's important for us to be able to interpret graphs, and it's easy to look at graphs and get overwhelmed, but a couple of things you want to do is you want to frame you want to really frame the overall picture. One, you want to say what am I actually going to be looking at? And if you see traces with different colors and things like that, sometimes you have to figure out how many things are going to be measured. So if we look on this graph, we see a red trace, and then we see a blue trace along with it. And so we recognize one is that we think, all right, here we go. We have two things that are being measured, and they're being measured over time. And we come over here and take a look at the horizontal scale. We go see it's in years, and it goes back to almost 500,000 years back. So we're not only looking at time, we're looking over a long period of time, because humankind at best is, has civilization is iffy well before, somewhere out in here back, it's not that much civilization going on. So we're looking at something that's more like geological time, because we are looking at 500,000 years back, and many civilizations could have come and gone in that period of time. So we see on the blue trace is looking at carbon dioxide concentration in the atmosphere as pulled out from different ice core samples, and in the red trace we have temperatures relative to today. So today's temperatures average around 0, and then we can see that they change on and off. So when you look at a graph, the idea is you want to get an idea of what's going. When you have a graph, you want to try to figure out what's actually going on in this thing. Are we looking at a trend, or do we have a cycle going on? And so if it's trend, things are going to either go up or they're going to go down. If you have cyclic behavior, you tend to see things repeating, and we can see here that clearly it looks like we have things going up and down and up and down. Because if they seem to go up steeply and come down slowly, and why it's going, but it's clear what we have here is something that represents a cyclic phenomena. In addition to that, we can see that the two trends are sort of related. There must be some correlation, because when the CO2 is high, the temperature is high, or another way to look at it is if the temperature is high, the CO2 is high. And that trend seems to correlate pretty well, and except that we get to this point at near current time where we really haven't actually have any red data to kind of track that at this point. So we can see that the two trends are correlated, and whether it's causation is a different issue. Final observation to make is we look at this. We see that the highest level that CO2 concentrations reached in the last 500,000 years or so has been under 300,000, or around 300,000 parts per million, or excuse me, 300 parts per million. So the maximum in this bump is around 280. It's around close to 300. This is like 270 or 280, 270, 280. And now at current time we see that it's actually soaring up towards 400 parts per million. So certainly over this last 500,000 years or so, the CO2 levels that we're seeing today are unprecedented. So we know the CO2 levels are high. We don't know. We could have there's two observations. One is that the CO2 is causing global warming. The other is that global warming cycles are leading to temperature changes. Either one would make sense. The fact of the matter is, though, we've never seen carbon dioxide levels as we have today. So it'll be interesting to see what happens to the global temperature, as time goes on. As a final note, of the last 18 years, we have seen there have been 15 of the hottest years observed to this point. So it's a busy slide, but there's a lot of information there. This is another. This slide I took out of the book, and I just wanted to remind you that sometimes things are messy. Here's our average temperature over the course of 100 years, and we see that in the beginning we have a lot of uncertainty in the data, which, this is only 50 years, 70, 100 years worth of data, so this is not really long term. It's like a few generations rather than a geological time. But we see that at earlier days there's a lot of uncertainty in the data, probably reflective of the issues we have in measuring temperature at the global surface, because global surface temperature is not an easy thing to measure, and statistically they've done a lot to make it more meaningful. However, we can see that in the last 50 or 60 years that certainly there seems to be a significant positive increase in temperature. If you disaggregate this data at the NOAA National Oceanographic and Aeronautic Administration website, you can see that the temperature increase is more significant over land than over water. And the one thing I'm looking for is this reflecting a global increase, or is it reflecting a climate change and increase in urbanization and greater energy use as we become more energy intensive? That is, we have more air conditioning, we have more people in small areas, more people with their own form of transportation. So this graph certainly tells us that there's more warming. There's been significant warming over the last 30 few years, but it's not clear to us where do we want to ascribe this to, because it is different for different locations. So there's a bit of doubt. There is certainly some information that we're having some sort of warming here, but this is more probably reflects local conditions rather than global climate change. Whereas the previous slide is more of a global climate change type sort of issue. But if we come back to this slide, we recognize that CO2 might be associated with a problem, and we might be able to have some influence on it by taking a look at the global carbon dioxide cycle, not just the carbon cycle. We recognize these items circled in blue are places where human activity is the most direct. We have things like burning fossil fuels, and we have deforestation. Deforestation happens because we need resources from the forest, and burning fossil fuels is because we need the energy. We recognize that both of these will increase with increasing temperature. As a result, with increasing population. As a result, we need to make certain that if we want to be able to moderate the amount of CO2 going into the atmosphere, to reduce the steady state concentration of carbon dioxide and reduce the amount of greenhouse effect, we need to do something about changing the amount of fossil fuels we burn and the deforestation, or find some way to increase one of these cycles that removes CO2 out of the ocean, either through reforestation, planting more crops for photosynthesis, and or finding some way to be able to deposit more in the ocean. So there are a lot of different issues, but probably we want to worry about at some point how are we going to replace some of these, and how much CO2 do we actually get out of burning fossil fuels. The fossil fuels are used for lots of reasons, and in industry, power heating, transportation, and residential, we can think of some replacements. But why do we have to specifically think of replacements? So why don't we take a break now, and you can go back and rehash this stuff. And what I'm going to say is that, and I'm going to come back to the next slide to talk about how we can compute how much carbon dioxide we're going to put into the atmosphere depending on which fuel we burn, for whatever purpose it is, whether it's for power heating stations, transportation, residential and commercial heating and use, or for industry for generating energy.